All right, so today we're going to look at section 7.8. It's titled Using Exponential and Logarithmic Functions. All right, so we do have two additional formulas we need to give in this section now that we have learned about E and its use in continuous growth or decay. And so we're going to give two functions for continuous exponential growth and continuous exponential decay. There's only one sign that's different between the two functions. Growth, we would have f of x equals a times e to the positive exponent of k times t. And then decay is just a negative exponent. So be f of x is equal to a times e to the negative k times t. So t is time, years, a is your initial value like it's been in previous section. The k here is a constant that represents our rate, like the rate of either growth or decay, depending on the case. So first, let's look at a population problem. We've dealt with growth and decay before, but it wasn't continuous growth. But many of the examples, many of the things we do are probably better modeled by continuous growth because you're not just getting growth at the end of the year, but it's kind of real life. It's going on at all times. So let's talk about the population of China. Oops. China. The population in 2007 was 1.32 billion. And in 2000, was 1.26 billion. The first question I'm going to pose is, what is the k value? We need to determine what that constant is. So we're going to determine the value of k. Is their population growing or growing or decaying? Growing. So it was larger in 2007 than it was in 2000. So we're going to go ahead and say it's growing exponentially at a constant rate. That we don't know what that rate is, though. That's what the first part is asking for, and then we would be able to apply that. So we recognize that it's growth as your first step. So we'll write down the growth model. And I want to think about what values I know. So do we know our initial amount? Do we know our initial time and our initial amount? Yeah, so we're going to go ahead and say that our initial time, we're going to start time in 2000. That's when our clock starts running here. That's the first data value we know. But I'm going to go ahead and call 2000 times 0. Is it okay to start time beginning there? Do we deal with smaller numbers? Yeah, I think that's okay. But I'm going to go ahead and make that notation or write that down. where t is the number of years since 2000. So we know the initial time, so then we know the initial amount. The initial amount was 1.26 billion. I don't really want to write billion. I would rather write 1.26. So I'm going to also make this notation up there that it's in billions. That way you don't have to write it, but we understand that our population is measured in billions. So in 2000, it was 1.26 billion. So 1.26 times e to the power of k times t, and we have the f of x here. So what else do we know? Well, we know what the population was in 2007. So that would mean time was 7 years. So 7k is what our exponent would be. And we know what our final answer. We know in 7 years it was 1.32 billion. So we know that's on the left side of the equation. And so we need to solve this equation. Because we're just trying to figure out what k is. Notice k is in an exponent. Therefore, it has been exponentiated. So we've solved those type of equations. We're just solving it in a word problem now. So to solve that, first, you need to divide away the 1.26. I am not going to bother simplifying that fraction or plugging it in the calculator to get a decimal. I'm just going to leave it as is for now. Eventually, I'll pull out the calculator, but not until the very end. So I'll just leave it as 1.32 over 1.26. So we've got rid of the 1.26, now have e to the 7k. So next I would like to get rid of the e. How do we get rid of e? We're going to log it with what base? Log with the base of e, so that's ln. So I would write ln in front of each side of the equation. So ln of the left side is equal to ln of the right side. What good does that do? Well, it cancels out the e on the right side. So now I have 7k is equal to the natural log of 1.32 over 1.26. And I'm trying to get k by itself, so I'll have one more thing to do. I'll have to divide by the 7 so that k is isolated, and then I can plug that into the calculator. So the natural log of 1.32 over 1.26, divide that by 7. We get a k value of 0.0066. I'll round it to that point. So 0.0066, that would be the k value. That answered the first question. And then I'm going to ask a follow-up question where we'll actually have to use that information. So here's the follow-up question. I'm going to say, when will their population reach 1.5 billion? Well, let's go back to the equation. We know what k is now, so I know a little bit more about the equation than I did before. So f of x is equal to my initial amount is the 1.26 to the power of, or e times e to the power of, well, now I know my k, 0.0066 t. So there's the equation that represents China's population growth. So if I'm trying to figure out when it's going to reach 1.5 billion, what do I do? Yeah, I know I want the answer to be 1.5 billion. I don't know when, so I don't know what t is. That's what I have to try to figure out. And now we have an exponential equation similar to the last one. So divide away the 1.26. Then I want to get rid of e, so I'll do the natural log of both sides. The natural log cancels out the e. And so to finish it off, I'll divide by the 0.0066. Plug that in the calculator. And we get that t is about 26.4. So knowing that t is about 26.4, I should be able to go and answer the question. The question was, when will the population reach 1.5 billion? We said t was the number of years since 2000. So that means it's going to hit 1.5 billion sometime in the year 2026, about halfway through the year. So in 2026 would be my answer to the question. Okay, so there's one example. We're going to do one other problem. This idea of continuous growth decay is often used in like the science world with like carbon dating. You've heard of carbon dating. Really, we can do it with different types of minerals or compounds or whatever. Carbon would be one thing, but we can do others. Oftentimes with those, you hear about half-life. And so we're going to take a look about at the idea of half-life. Let's talk about our book. I'm just going to steal a problem from the book. They talk about plutonium-239. They make this claim that the half-life of plutonium-239 is 24,000 years. What does that mean? Well, if you have some plutonium-239, it takes 24,000 years before you have half of that amount. What happens to it in the meantime? I don't know. I'll talk to a science teacher to find out. I don't know the answer to that exactly, but maybe some of you do. But that's how much time it takes for it to become half of what it was. And this is applicable because what's happening exponentially? Is it growing or decaying? It's decaying because it's becoming half of what it was. So it's becoming smaller. This is an exponential decay model. It is continuous. So we use the model that has the negative exponent. Let's go ahead and figure out what K is. Let's find the equation that models plutonium-239 is really what I'm trying to get to. So that's all I'm giving you. We have to come up with the equation from there. Well, the equation uses an initial amount and a final amount. Do I know the initial amount? I know how much plutonium there was initially. It doesn't say, does it? It doesn't give you an initial amount. It doesn't need to give you an initial amount. Think about what you're going to do to solve this problem. Don't write this part down, but just watch along for a second. Eventually, you're going to divide by the A, right? And you would divide the other side by the A. So you're going to end up with the final amount divided by the initial amount. If I'm talking about half-life, what is my final amount divided by the initial amount? It's half. If I started with 100, I end with 50. 50 divided by 100, 50 divided by 100 is 1/2. Anytime you're dealing with half-life, we can put 1/2 there, and we divided away the A. The A is gone. I really just have E to the power of negative K times T, but I do know my time in this case. It took 24,000 years for it to become half of what it was. So by getting rid of the A, I know it's a 0.5 over there. It's true for any half-life problem. So now we solve this once again by using the natural log. You see that the last section is pretty important to being successful in this section. So we ln both sides. So I get that the natural log of 0.5 is equal to negative 24,000 K. So we would then divide by negative 24,000. So plug in the calculator. Natural log of 0.5 divided by negative 24,000. I get about 1.254. Let's see. Did I do something wrong? This is not the same answer I had before. The book. Where did I make a mistake? No. Oh, I did log. I didn't do ln. That's why. Okay, let's try that again. So 2.888. But if you keep looking at the calculator, at the end it says E negative 5. That means times 10 to the negative 5th. It means it's in scientific notation. So we have to catch that E at the end. There's our K value. So my equation for plutonium-239 right, 1, 2, 3, 4, 5. Yep, okay. Here's the equation that we could use to do questions about plutonium-239. Yeah, depending on what the questions. they might ask you a follow-up question. They might only ask what K is. They might ask what the equation is, or maybe they then say, okay, now let's say you've got, I don't know, 100 pounds of plutonium-239. How much will you have in 10,000 years? We could ask questions like that. So let's do that problem and just see what we get. If we have 100 pounds of plutonium 239, how much will there be in 10,000 years? More or less than 50 pounds. Remember, it takes 24,000 years for it to be half. And we have less than 24,000 years, so we will not have lost half of it yet. Okay, let's use the equation. Let's plug it in. We don't know what our final amount is. That's what the question is asking. We have an initial amount of 100. $10,000 years. Oh, see, you don't even have to do any logs or anything. You can just plug that in the calculator. We would get about 74.98, basically 75 pounds. All right. If you look at the calendar for this section, it lists the assignment really strangely. I didn't make the calendar, and I don't really understand what the goal was, but clearly doesn't make sense as it's written. So the assignment, I guess it begins on page 513. And from the best that I can discern, it should be problems 5 through 8 and 10. The way it's written is it says 5A and then 5B through 8 and 10. So I don't know why they separate 5A and 5B. Seems like it should be all of 5 through 8 through 10. So that's what I'm going to have you do for the assignment. K is the rate. Yep, K is like the rate it's growing or decaying. Right now it's written as a decimal, not as a percent, but yep, that would be your rate.